Alright, welcome class. This is the day one of our at-home learning. It's going to be a little tough. You're going to have to bear with me. I'm still getting used to all this. Y'all are still going to be getting used to all this. Let me know if there's any sound problems, anything like that. I'll try and fix them as I upload more videos. This video today will be in two parts. Part 1 and part 2, I'll make sure to put some type of note somewhere where the parts can separate. Feel free to do them all in one day. That's why they can be done as one video. But if you want to break them into 2 days, that works as well. The homeworks will also be split in 2 parts to fit that mold. Okay, so today we're starting with Taylor Polynomials and Taylor Series. We're going to start with this by looking at two functions on our calculators. So if you have your calculator at home, you can look at it yourself, or you can look at it with me. Give me a second while I change this back to a normal function. Oops. All right, so we're going to compare sine of x to the graph of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So x minus x to the 3rd divided by 3 factorial is the same as saying 6 plus x to the 5th divided by 5 factorial, which is the same as saying 120. We're going to look at these graphs and compare them. And what we notice is that right around this area right here, this is a pretty accurate representation of the graph of sine of x. But if we were to take the time to zoom out a little bit more, we'd notice that it doesn't stay a great approximation. So let me zoom out a little bit. We notice that it's only a good approximation right there. This is the whole idea behind Taylor series and Taylor polynomials. They are approximations for whole functions that we may not normally have a polynomial for. So we start with the definition of an nth degree Taylor polynomial. If f has an n number of derivatives, that means as many derivatives as you want this degree polynomial to be, and x equals to c, or at x equals to c, then the polynomial p sub n of x equals f of c times, or plus f prime of c times x minus c, plus f double prime of c times x minus c squared over 2 factorial, f triple prime of c times x minus c cubed over 3 factorial, and so on and so forth till you get to the nth derivative or nth polynomial. That many derivatives, x minus c to the nth power over n factorial. This is what we call the nth degree Taylor polynomial for f at c, named after an English mathematician, Brooke Taylor. If we end up doing this with c equals to 0, you'll notice that this changes only slightly in that we now have 0 for c, and so it's f of 0, f prime of 0, and instead of x minus c, x minus 0, which just gives us x squared, x cubed, and so on and so forth. This is what we call a Maclaurin polynomial. Now what these are used for is these can be used to approximate other functions that we may not be able to accurately find values for. For example, sine of x, like we did just up here. Okay, so let's look at this in an actual problem. We want a function f which has a continuous derivative, and that f of 2 equals 3, f prime of 2 equals negative 4, f second prime of 2 equals 7, f triple prime of 2 equals negative 5, and we want the third degree polynomial centered at 2. Well, third degree means we want to do it so many times that we get to the third power and the third derivative. That's what we're meaning by third degree. Well, down here, we see that they give us first power, second power, original, first degree, second degree, third degree. Okay, so we see all these things already being given to us. So at this point, it just comes down to plugging into the formula. So we have f of 2 goes right there. F prime of 2 goes right there. Double prime right there. Triple prime right there, with 2 going in for all these c's here. Okay, so let's actually do this and write this out. So, we want it centered at 2. That's already given by all these values being 2. So we start with f of 2. F of 2 plus f prime of 2 times x minus 2. Bear with me with the writing. I'm still getting used to writing with the stylus. Plus f double prime of 2 times x minus 2 squared. Now that we've got to the second derivative, we're going to use the second power, and over 2 factorial plus f triple prime of 2 times x minus 2 cubed over 3 factorial. Now, this is it just written out without actually plugging anything in, so now we're going to actually plug some things in. Okay, so f of 2 is equal to 3 plus f prime of 2, which is negative 4, times x minus 2, plus f double prime of 2, which is 7, times x minus 2 squared over 2 factorial, which is just 2, plus f triple prime of 2, which is negative 5, times x minus 2 cubed over 3 factorial, which is 6. We're not asking you to simplify this anymore. We're just saying this is the third degree polynomial for f of x. And it's a good approximation for what f of x is when you pick a number close to 2. Okay? Let's look at another one with this. This time we have the nth degree Taylor polynomial with n being 4 for f of x equals e to the 3x at 2. Now this one doesn't give us much information, but a few things it does tell us. N is equal to 4, which means we're going to do fourth derivative. Once again, bear with my writing. And we're centered at 2, so this means this is what c is equal to. So we first need to do the fourth derivative, and then we need to set up our equation. So let's start with the fourth derivative part. This is the easiest part. So we'll start with f of x, and that's just going to be, let me write that a little bit better, see if I can get it down a little bit better. So we'll start with f of x. Let me see. And that equals e to the 3x. Then we'll move on to f prime of x. This is the first derivative. Well, derivative to the outside is e to the 3x. Derivative to the inside is 3. So 3e 3x. Next derivative is the second derivative. That gives us 9e to the 3x. Then we have the third derivative. So that gives us 27e to the 3x. And then lastly, we're finally at the fourth derivative. I'm just going to put a 4 here so I don't have to write tally marks. And the fourth derivative would be 27 times 3. Y'all know my math skills aren't great, but we have 1, here the 2, 6, 7, 8, 81 e to the 3x. Okay? So these are our fourth derivatives. Now we want it centered at 2, which means if we look back at our formula we had earlier, that needed f of 2, f prime of 2, f double prime of 2, PS 2 is what our c value is. So now we're going to take all of these and we're going to actually plug in 2 to them. So we're going to start with f of 2. So that's e to the 6th f prime of 2. That's e to the 3e to the 6th, sorry. Triple prime of 2, or double prime of 2. 9e to the 6th. Triple prime. 27e to the 6th. And then fourth derivative is 81e to the 6th. Now, that got really messy right there at the end. Let me see if I can sharpen that up a little bit. E to the 6th. There we go. A little bit better. All right, so these are the values we want to end up keeping. So here's what I'm going to do. I'm going to erase all of this, because we don't care as much about these anymore. More about the values when 2 is plugged in. And we're just going to move, let's see, is there a way that I can move all of these? There is not. We're just going to change the slide for now, and we'll come back to it. Okay, so now let's start plugging these into the formula for the Taylor polynomial. So we have f of 2 first. Well, f of 2 we said was e to the 6th, plus f of 2, or f prime of 2 times x minus 2. F prime of 2 we said was 3e to the 6th, so 3e to the 6th times x minus 2, plus then we have f double prime of 2, so 9e to the 6th times x minus 2 squared over 2 factorial, which is 2. Now we do the third derivative, f triple prime, so 27e to the 6th times x minus 2 cubed over 3 factorial, which is the same thing as saying 6. And then we get to where I'm running out of space, so we'll add another line down here. That is 81e to the 6th times x minus 2 to the 4th power over 4 factorial, which is 24. Now this one we can simplify a little bit. So we're going to simplify this right here and this right here, but that's about it. So 27 over 6 ends up giving us 9 over 2, so another 9 over 2 with that one. And 81 over 24 ends up giving us 27 over 8, if I did my math right. So we need to simplify those. I'm running out of space here. I don't want to rewrite the whole thing, but you do need to simplify this one. And this one over here. Okay? Alrighty. So let's keep moving. Now that we've looked at a few of those, let's look at a Maclaurin one. Now, this one gives us, if we compare, a little bit less information than the first one. It doesn't tell us what we're centered at. But that's because, remember, Maclaurin means we are centered at 0. Or in other words, 0 is our C. Now, we don't have to remember that if we actually remember that Maclaurin series, if we go back up here, Maclaurin series just have 0 in already. And so we just don't do the minus C, we just work with it from there. So we're looking at the 5th degree, which means we need 5 derivatives for sine. Now, some of you are going to get a little frustrated with doing all these derivatives, and I'm going to get a little frustrated just because I'm going to have to write all this, but we will get through it together. So f of x equals sine of x, f prime of x equals cosine of x, double prime equals negative sine, so on and so forth. So triple equals negative cosine, fourth equals positive sine, and then fifth equals cosine again. But here's the beauty of these. If we notice, since we're centered at 0, that means we're doing f of 0, f prime of 0, and look what happens to all these that have sine in them. This one is 0, this one's 0, this one's 0, and all of the ones with cosine are just different variations on 1. This one's 1, -1, and 1. So this becomes super easy to plug in when we think about what formula we're actually using. So if we go back up here to the formula for the Maclaurin, this is f of 0, f prime of 0, f double prime of 0, f triple prime of 0. Well, we've already found all those. So let's look at this. Let me give myself some more room to write down here. Okay, so we start with f of 0, which was just 0, plus f prime of 0, which is 1, times x, plus f double prime of 0, which is back to 0, times x squared over 2 factorial, but because this was just 0, that just goes to 0, plus f triple prime of 0, which is -1, times x cubed over 3 factorial, plus f to the fourth derivative of 0. Well, that's just back to 0 again. So we have 0x to the fourth over 4 factorial. And then plus, finally, f to the fifth derivative of x, which is cosine, which would be 1. So 1x to the fifth over 5 factorial. Now, after simplifying all of this down, what we end up getting... Whoops. I think I went too many, but that's okay. Oh, there we go. All right, what we end up getting is that series that we started with that when we first looked at the calculator. X minus x cubed over 3 factorial, which was 6, plus x to the fifth over 5 factorial, which is 120. And we see, now this is all coming together, how this was a good approximation for sine right around 0. The more terms we add to this polynomial, if we were to just keep going, the more accurate it would become in how close it is to sine of x. Okay? Now, what we can do with this is we can now find approximations. Now, these would be done with our calculators. I will let you do these on your own. These right here. Okay? But it should be easy enough to see that our approximation for 1.4 and our actual value of 1.4, this will be 1.4 plus, minus. Let me get that right. This will be 1.4 minus 1.4 cubed over 3 factorial plus 1.4 to the fifth over 5 factorial. And then this right here, this is the actual value of f, which f is just sine of x. So this is just sine of 1.4. And what we're looking at here is what is the error in our approximation? How close is this answer to this answer? This is not something I need to go over with you. You can just plug it in and see it, but we symbolize that error with f of 1.4 minus p sub 5 of 1.4. So this being the approximation and this being the actual value. Okay? And so you can see with that error. If you ever see this, kind of like right here, you'll know that that's what it's asking for. It's just asking for the error between your approximation and the actual value. Okay? Now, after you do that, you can kind of look at this one and get a good thought about this. What you should see is that this error is actually smaller than this error. And the reason this is because this one is closer to the center. As we saw when we graphed it, the closer we were to that center point, the more accurate it would be. Okay, so 1.4 is about right here, whereas 2.1 is about right here. And so you see there's a good difference there between which one is more accurate. Now, if we use our polynomial to estimate 2.7, we've now gotten even further away from the center, so you should be able to make a good approximation about what happens there. It should get further away from, or bigger in an error. Okay, so that is the end of part 1. On your homework, you'll see a separation between part 1 and part 2. This video is still going to be one video, but keep in mind that if you wanted to separate it into 2 parts so you're not doing as much in one day, that is completely fine. Okay, so moving on to part 2. So we said we said earlier that these were the formulas for an nth degree Taylor and Maclaurin polynomial. Now, this leads us to what we call Taylor's theorem. We're not going to do too much with it today, but this is an important theorem to know later. So go ahead and write it down, pause the video, write this down. And this says that R sub n is what we would call the error of the next term. Now, once again, this is a lot more. We're going to talk about Lagrange at the end of this unit. This is probably going to be the toughest topic to learn outside of being in class and seeing it, but we're going to do our best and we'll get through it. This is going to come more in depth later. For now, we're just going to look at more things that come together with Taylor polynomials. Okay, so let's look at this first example. We have a polynomial sub 2, meaning it's the second degree polynomial for a Taylor polynomial that's centered around 0. So really it's a Maclaurin polynomial. We're asking what are the signs of A, B, and C, all right, to the picture to the right. I ask you right now to go ahead and pause the video and try yourself to see if you can figure these out. Okay, so let's discuss what you might have found. Okay, so if we look at this, we know that each of these numbers represent something important in the formula. If we look back up, since this is really a Maclaurin polynomial, these 3 numbers represent these 3 values of the derivative. 1, 2, 3. Okay, so we're looking for what are the signs of these 3. Well, that means that A, this first number here, this has to be, and I'm going to try and get really precise with this, f of 0. Okay? And I'm looking like I'm running out of space, so I'll write this under here. So A has to equal f of 0. Now we can look at our graph and see, okay, at 0, what sign is this going to be? Well, this is just the value at 0, and this is greater than 0, so that means this has to be positive. Well, now we look at B. Well, if we look back at the formula for a Maclaurin polynomial, this is going to be f prime of 0, which in other words is saying what is the slope at 0. When we look at it here, we have an increasing function, which means our slope has to also be positive. And lastly, we look at C, which is f triple prime at 0. Now this, it's been a while since we looked at this, but this is actually the concavity. So if this is the third derivative, that means we're looking at the concavity at this point. Well, the concavity at this point, it is bending downwards. We see that it's almost trying to make a U shape there. And so that means we're going to have a negative sign there. Okay, so these are just examples of the type of problems that can be asked with relation to Taylor polynomials. Some of them not always being super obvious to what you would normally think. Okay, what about these two? All right, so let's look at this next one. Suppose that a function f of x is approximated near x equals 4 by a third degree Taylor polynomial. P sub 3 of x equals 2 minus 5 x minus 4 squared plus 8 x minus 4 cubed. Find the value of f of 4, f prime of 4, f double prime of 4, and f triple prime of 4. I'll give you all a second to try and figure this out on your own first. Go ahead and pause your video and think about it. Okay, let's look at this. Now, we know from our, from our formula up here that f of 0 is the constant, f prime of 0 goes with x, f double prime of 0 is divided by 2 and goes with x squared, f triple prime of 0 is divided by 3 and goes with x cubed. That's for a Maclaurin. For a Taylor, it's very similar. All that's going to happen is it's going to be combined with x minus c, x minus c, and x minus c. So let's look at what we have in our problem. Let's start with the constant. Well, here's our constant. That's by itself, so that has to be f of 4. Now let's look at the part with x minus c. Well, that's what would normally go with here, x minus c. The problem is there's no x minus c in there, which means f prime of 4 had to equal 0. Sorry, this equals 2. Whoops, not 0. 2. Okay, now let's move on to the third derivative, or second derivative. F double prime of 4. This is usually multiplied by x minus c squared and divided by 2. Well, 5 is right here, but to end up with just 5 there and no denominator, we'd also have to multiply that by 2. So what number would actually go there? Well, that's 10. And we also have to look at the sign as well. This is a negative 5, so that becomes a negative 10. And lastly, we have the third derivative. Similar thing happens here. Normally this would go with x minus c cubed and divide by 6. And so we have an 8 right here. But to get it to just end up with 8, we'd have to multiply by 6. So the number that's actually there is 8 times 6, which is 48. Okay? Alright, so let's move on to the second part of this problem. Does f have a local maximum, a local minimum, or neither at x equals 4? Well, this is where things get a little bit interesting, because this calls back to something we haven't done for a while in the second derivative test. So or not with your partner, you don't have partners, but go ahead and think about this yourself, and then we'll look at it together. All right, so let's look at this one. So let's start with the local maximum, or local minimum, or neither. Let's start with where we get this idea from. We see that the first derivative is equal to 0. And we remember that if f prime of c is 0, then we have two things that could happen. If f double prime of c is greater than 0, which means f double prime of c is positive, then we have a min. And if f double prime of c is negative, then we have a max. Well, we already have enough information with this. We are already given f double prime of c. Well, it is negative, so that means we have a max there. All right? So let's keep moving. All right, the function f has derivatives for all orders, or of all orders for all real numbers x. Assume f of 3 equals negative 4, f prime of 3 equals 2, f double prime of 3 equals 7, and f triple prime of 3 equals negative 5. Write the third degree Taylor polynomial. This should be easy by this point. It's just plug it into the formula. So we have negative 4 plus 2 times x minus 3 plus 7 times x minus 3 squared over 2 factorial minus, minus 5 times x minus 3 cubed over 3 factorial. Okay? Pretty straightforward there. All right? Now we have this next part. Write the fourth degree Taylor polynomial for g of x equal to f of x squared plus 3 centered about 0. Now this seems like a pretty complicated situation, but we already have a polynomial here, and all we're doing is plugging in x squared plus 3. Let's see what happens when we plug this into our polynomial. So we have negative 4 plus 2 times x squared plus 3 minus 3 plus 7 over 2 times x squared plus 3 minus 3 squared minus 5 over 6 times x squared plus 3 minus 3 cubed. Well, what we notice is this starts to work out in our favor. Negative 4 plus 2x squared, that's centered at 0 already. Now we have no c in there with x. Plus 7 over 2 times x squared squared, which gives us x to the fourth. We now have the fourth degree Taylor polynomial. We didn't even need the rest of this. Not even needed. We have the fourth degree Taylor polynomial. This is our approximation for g of x. Approximation. Okay. So let's clear this. Now, so tonight you'll work on your homework. Well, not really homework. As of right now, I have no plan to grade it. Please email me any questions. I'll try and have a time set up, posted on It's Learning, where you can ask me questions through what we're probably going to use is Zoom. So we'll get all that set up then. Y'all have a great day. All right, so let's look at this next one. Suppose that a function f of x is approximated near x equals 4 by a third degree Taylor polynomial. P sub 3 of x equals 2 minus 5 x minus 4 squared plus 8 x minus 4 cubed. Find the value of f of 4, f prime of 4, f double prime of 4, and f triple prime of 4. I'll give you all a second to try and figure this out on your own first. Go ahead and pause your video and think about it. Okay, let's look at this. Now, we know from our, from our formula up here that f of 0 is the constant, f prime of 0 goes with x, f double prime of 0 is divided by 2 and goes with x squared, f triple prime of 0 is divided by 3 and goes with x cubed. That's for a Maclaurin. For a Taylor, it's very similar. All that's going to happen is it's going to be combined with x minus c, and x minus c. So let's look at what we have in our problem. Let's start with a constant. Well, here's our constant. That's by itself, so that has to be f of 4. Now let's look at the part with x minus c. Well, that's what would normally go with here, x minus c. The problem is there's no x minus c in there, which means f prime of 4 had to equal 0. Sorry, this equals 2. Whoops, not 0. 2. Okay, now let's move on to the third derivative, or second derivative. F double prime of 4. This is usually multiplied by x minus c squared and divided by 2. Well, 5 is right here, but to end up with just 5 there and no denominator, we'd also have to multiply that by 2. So what number would actually go there? Well, that's 10. And we also have to look at the sign as well. This is a negative 5, so that becomes a negative 10. And lastly, we have the third derivative. Similar thing happens here. Normally this would go with x minus c cubed and divide by 6. And so we have an 8 right here. But to get it to just end up with 8, we'd have to multiply by 6. So the number that's actually there is 8 times 6, which is 48. Okay? Alright, so let's move on to the second part of this problem. Does f have a local maximum, a local minimum, or neither at x equals 4? Well, this is where things get a little bit interesting, because this calls back to something we haven't done for a while in the second derivative test. So or not with your partner, you don't have partners, but go ahead and think about this yourself, and then we'll look at it together. All right, so let's look at this one. So let's start with the local maximum, or local minimum, or neither. Let's start with where we get this idea from. We see that the first derivative is equal to 0. And we remember that if f prime of c is 0, then we have two things that could happen. If f double prime of c is greater than 0, which means f double prime of c is positive, then we have a min. And if f double prime of c is negative, then we have a max. Well, we already have enough information with this. We are already given f double prime of c. Well, it is negative, so that means we have a max there. All right? Let's keep going. And